from this gravity center, the distance between the center of the front wheel, this is actually given by LA. And from the gravity center, whatever is the distance of the back wheel or rear wheel, so this distance is called as LB. So LB is a greater distance. And this LA plus LB together, that is actually is equal to L, and L is called as actually the wheelbase. So how much is the distance between the two centers of two wheels? Then there is another physical parameter which is very important. That is actually called as Hg. That is the height of gravity center. That means what is the height of the CG of the vehicle from the ground. Okay, so that thing is also very much important. So with all this and there are some friction generated, you are finding that if the vehicle is rotating in anti-clockwise direction, so this is the direction of friction, which is called as FBF, and this is called as FBR. FBR stands for friction force at rear wheel. FBF stands for friction force at the front wheel. WF and WR are there, that is the weight at the front and weight at the rear, and these are the parameters, that is WF, WR, LA, LBL. There's a 5 2 frictions, 8 9, and there are 3 2 M's and 1 Hg. So these are the 10 parameters actually. If you see the previous slide, all those 10 parameters actually within this L, LA and LB, they are hidden. Okay, and within this FR actually the FB, FR, all those things are there. So mainly there are 7 parameters, that is mass, friction coefficient, aerodynamic drag, area, that is the LA, that is the wheelbase, distance between two wheels, and height of the gravity of the center. So these are the 6 parameters actually which are helping us to design how much will be the force for braking. So here the vehicle parameters are given. Here you can see that is mass, rolling resistance, aerodynamic drag, front area, wheel base, distance from gravity center to the wheel center, and gravity center height. All these things are given with units. So, and what are the standard values of them, that is shown in this. Actually, I think this is table 14.1 in the book. So just see that. So this will be helping you to understand or design or calculate for brake value or friction value in a better manner. Now there is something, a very interesting fact, and this is a very good nice graph actually, which is called as braking energy distribution over vehicle speed in FTP 75 urban drive. So in urban drive, what we are finding is, if you see the x-axis is a vehicle speed and y-axis, that is a braking energy percentage distribution over wheel speed, and that is actually given in percentage. That means whenever we are finding the vehicle speed is within kind of a 20 kilometer to 50, 45, 50 kilometer, this range. Okay, in that case, if we are putting the brake on the vehicles, that is actually generating more amount of energy compared to the vehicle has a very high speed, 50, 60, 80, 90, 100 kilometers. In that case, if we are putting brake, in that case more energy is not generated. So that is what is saying as braking energy versus vehicle speed. So what is the relationship between braking energy to be put and vehicle speed? So braking energy distribution over vehicle speed in typical urban drive cycles is useful information for the design and control of regenerative brake system. In the speed range in which the braking energy is most dissipated, the operating efficiency of the electric motor functioning as a generator may be most concerned. So in this case, the most concern in vehicle speed is actually from around 15-20 up to 45-50 kilometer per hour. So this line is very important in this speed range, that is 15-20 up to 45-50, in which the braking energy is most dissipated. That means if a vehicle is running with in this range, in that case, if you are just trying to stop the vehicle, in that case most energy is dissipated. Okay, so this is of most concern. In other speed ranges, is regenerative braking may be abundant. So we can get maximum amount of energy generation through regenerative braking if braking energy is high. So more is the brake energy, more regenerative action or more regenerative energy can be generated. So that is happening in between 15 to 20 kilometer per hour up to 45 to 50 kilometer per hour. So this is saying that in other speed ranges, that means greater than 45-50 or less than 15-20, that means these are the range in which energy recovery is very less. So most amount of energy can be recovered in between vehicle speed of 15-20 up to 45 to 50 kilometer per hour. The braking power versus vehicle speed profile, which is shown next, naturally match the power speed characteristic of the motor. So in that, the power is proportional to the speed from zero speed to base speed. There is a constant torque and is a constant beyond the base speed. So thus electric motors do not need a special design and control for regenerative braking purposes. So whatever we are doing, whatever vehicle braking we are doing, and whatever motor is being used for generating the tractional torque or the braking torque. So from the same motors we can achieve the highest amount of regenerative braking. So here another graph is there. So these graphs are actually very much important to understand the overall regenerative braking action. So this is a graph between vehicle speed. So previous graph was between vehicle speed and braking energy percentage, and we found out that 15 to 20 up to 45 to 50. This is the range in between which we can generate best amount of regenerative braking. This is a graph which shows that the braking energy dissipated in a speed range that is less than in given speed. So in less a given speed, that is around 15 kilometer per hour, braking energy dissipated is actually very less. So these two figures indicate that only 10% of the total energy is dissipated in the speed range below 15 kilometer per hour. So very important line. So it indicates that only 10% of the total braking energy is dissipated in the speed range below 15 km per hour. So there is a table which shows that the braking energy dissipated in the speed range below 15 km per hour while driving in other typical urban cities. So this is the plan. So these are different plans. So FTP in New York, LA stands for maybe Los Angeles. So this is US, this is the whole New York City and other thing. So braking energy less than 15 kilometer per hour percentage. So we are finding that braking energy less than 15 kilometer per hour is 10.93%. So here also you are finding that below this 15 kilometer per hour, 10.93% of energy is being dissipated. Braking energy versus braking power. So this is another graph. So braking energy percentage in range that is greater than the power is shown in the horizontal axis. So braking energy percent in that range which is greater than the horizontal power is shown in the horizontal axis. So braking energy versus braking power. So what is the difference between energy and power? Energy means whatever work you are doing, and power means work done per time. Okay. So if in very short time we have to put huge amount of braking energies to stop a vehicle, in that case we say that the braking power is too high. So braking energy versus braking power is another important thing. Understanding braking energy versus braking power in a typical drive cycle is a very helpful in the power capacity design of the electric motor on the broad energy storage, so that they can recover most of the braking energy without oversized design. That means if we understand this braking energy versus braking power graph, we will be able to design or will be able to get the same kind of regenerative braking by using the same motor. Some special oversized motor is not to be designed. So figure shows that the braking simulation result for a while driving in an urban drive cycle. So this is the urban drive cycle thing. So x-axis is braking power, how much braking power you are applying, and y-axis is braking energy percentage in braking power range, which is greater than the power on x-axis. So a certain threshold power is defined. So that is given by this horizontal line. So you are finding that for brake power in between 0 almost up to 14.5, okay, we are generating greater power, greater energy. And after that from 14 to 20, so in that brake power range we are actually getting less energy. So for less power we are getting more energy, almost 100%, and it is almost falling to 15%, and above 15%, below 15% brake energy is being produced for higher speed. So figure shows the braking simulation result while driving in a urban drive cycle. So around 15%. So this power is actually 15%. Around 50% of the total braking energy dissipated in the braking power range greater than 14.4 kilowatt hour. So this is actually 14.4 kilowatt hour. Greater than that, this much energy is actually 15%. So how much energy is dissipated below 14.4 kilowatt hour, and how much energy is dissipated above the power of 14.4 kilowatt. So we are finding that below 14.4 kilowatt hour energy, sorry, power, almost 85% energy is dissipated. And we are saying that if you are trying to increase the brake power at that time, energy becomes lesser. So they are saying that this results implies that 15 kilowatt electric motor can recover almost 85% of the braking energy. So very important line that 15 kilowatt hour electric motor can recover about 85% of the total braking energy in this driver cycle. So figure shows results for urban drive cycles, which also indicates the braking power range in which 85% of the total braking energy is dissipated. So these data are good indicators of the design of the power capacity of the electric motor and the onboard energy storage from a braking point of view. Now, finally, we have come to the slide where braking energy on front and rear axle. So this is actually the big question, that how to distribute the braking energy on front and rear axle, because we cannot apply braking power only for front axle. So front and rear axle both should be given braking power constantly. So here the deceleration rate is given. So in which rate the deceleration of the car is happening. So deceleration is increasing means actually the vehicle stops here completely. Okay, and y-axis is actually braking energy for deceleration. So we are finding that as deceleration is increasing, braking power, braking energy is also increasing. That means more and more energy you are applying, the car is going towards the stop stage. So what it says is the braking performance for passenger cars require the braking force distribution in the front and rear axle to be below the curve but above the braking regulation curve. Okay, so below, it should be below the curve and above the braking regulation curve. So this requirement implies that most of the braking force is applied on the front axle. Okay, so most of the braking we are applying on the front axle, and that's why the car actually it takes a circle. Okay, so it skids, the back tire skids. Consequently, regenerative braking on the front axle is better than on the rear axle. However, for other kinds of vehicles such as trucks, the rear axle may be better. Whenever things are very heavy, trucks and all which are fully loaded, for that uh, rear axle braking is better, and for passenger vehicles, front axle braking is better. Okay, so this is a graph which actually maximum deceleration rate and braking energy dissipated in deceleration range for less than 0.15 gram. So last slide for today that we are going to see is the brake system of EV, HEV, and FCV. So there are mainly two requirements we will see, and there is a small discussion, and we'll end with that. What is that? Regenerative braking in EV, HEV, and FCV introduces slight complexity to the braking system design, and there occurs two questions. So already it is discussed. First question is how to distribute the total required braking force among the regenerative braking and frictional braking to recover as much as braking energy as possible. So more than recovering energy, first ask or first task is to braking forces to be distributed among all the four wheels or in front and rear. How to distribute the total required braking force among regenerative braking and frictional braking to recover as much braking energy as possible. So frictional braking is applied to the front and rear, and regenerative braking is actually obtained from the vehicle within a certain range, a certain speed range. So frictional braking to decelerate the car and regenerative braking for energy generation, both should happen properly. Second thing is how to distribute the total braking force on the front and rear axles to achieve the stable braking performance. So first point is how to distribute between regenerative braking and frictional braking. So frictional braking is actually mechanical braking. It is not generating any energy. Regenerative braking is actually generating energy within that 15 to 20 up to 45 to 50 kilometer per hour range. And second question is how to distribute the total braking force on the front and rear axle to achieve the stable braking performance. So usually regenerative braking is effective only for the drive axle, that is the front axle in case of passenger cars. The electric motor must be controlled to produce the proper amount of braking force to recover as much braking energy as possible. Now, last conclusion. So, before we go for the bigger systems for regenerative braking, so there are two systems we will discuss. Which are the two systems we will see here? So, next day we will discuss these two systems. So, one is parallel hybrid brake system, and another one is fully controllable hybrid brake system. So, a little bit of knowledge about that, and we will stop this session. So also total braking force must be sufficient to meet vehicle deceleration commanded by the driver. So driver is actually pushing the brake to decelerate the vehicle and to stop it. So two configurations of hybrid brake systems are discussed with their corresponding design and control principles. We will see it tomorrow. First one is the parallel hybrid brake system. So what is that? It has a simple structure and control, and it retains all the major components of the conventional braking. So parallel hybrid brake system is a very simple brake system, traditional orthodox brake system, which we have been using for so many years. The other one is fully controllable hybrid brake system. So what is that? It can fully control the braking force for the individual wheels, thus greatly enhancing the vehicle's braking performance on all type of roads. So these are the two types of brakings, and how to generate the electricity back from this frictional braking things we will see on the next day. That's all. Thank you.